Hi everyone. Today we're going to cover predicting survival on the Titanic using logistic regression. So we finally made it to our first classifier, and that's going to be logistic regression. Um, so I'm going to make a very simple logistic regression model. My model is going to use the independent variables sex and age to predict the dependent variable survived. There are a whole bunch of other variables in this data set that you could and should use. But that's going to be your assignment, so I don't want to do that for you right now. Okay, so first I have to do just a little bit of data prep to get my model, to get my data ready to be trained into a model. This stuff you've seen before. We're going to use pandas again. I'm going to create a data frame from pandas using train.csv. And then here are all the column names, just in case you forgot. So as I said before, I'm going to create a data frame, and I'm going to only put the three variables that I care about in it, which are sex, age, and survived. So you can see that I'm indexing my original data frame, and I'm saying, give me the entire sex column and put that in my new one that I've called X, and I've given it a similar name. Same thing with age, and then lastly survived, which is going to be my dependent variable. All right. In my data, I have a bunch of places where I have missing data. So my strategy for handling missing data right now, today, is going to be to just drop those rows. So I'm going to lose a whole bunch of information when I do that. That's probably not the best strategy. The best strategy would be to do something like mean imputation, or even a little bit more intelligent mean imputation or imputed value using another model. But for now, I'm just going to drop these. All right. So then let's talk about survived. Survived is my dependent variable y, and just to make things a little bit easier so I don't have to slice x a bunch of different times, I'm going to take x survived, I'm going to assign it to my variable y, and then I'm just going to drop it out of x. I'm going to say I don't want that in there anymore, so now at this point x will only contain age and sex. All right, so we have one other problem. If you remember the data, our column sex actually has two text fields in it. The text fields are male or female. So we need to convert that to a number. And if you remember, the way that we talked about doing that last week was called one-hot encoding. You can refer back to last week's lecture if you want kind of a reminder on that. I'm going to use Panda's feature called get dummies, which is kind of a silly name, but dummy variables are another way, or indicator variables are another name for one-hot encoding. And you can see that if I call that on the sex column, I get back two new columns, female and male, and I just get a 0 or a 1. So for example, person 0 was male, so they have a 0 in the female column and a 1 in the male column. So I can use that. One thing that we do have to be very careful about, though, is when we have a indicator variable like this, it's really important that we drop one of the categories, or otherwise we're going to end up with perfectly collinear variables, which are bad. Trust me on it, they're bad. So what I'll do is I will set x.sex equal to only the female column. And so what that does for a binomial indicator variable is it gives me now, if there's a 1 in that column, then I know that the person was female, and if there's a 0 in that column, I know that the person was male. All right. One more thing to do at this point is, remember from last week, we have to scale our features. So this is the z-transform step that we talked about last week. So I'm going to use scikit-learn standard scalar, and I'll just set x to scalar.fitTransformX. All right. Very last thing is I'm going to use test-train-split to split my data into a testing set and a training set. The training set will be used to train the model, and the testing set will be used to test the model. You can see here that I've set test size equal to 0.2. And what that's going to do is that's going to make it so that my test set is 20% of my entire data set. All right. So at this point, I have a training set defined, and I have a testing set defined. So now I can go ahead and start creating a model. But one more thing. Let's say that I create a logistic regression model, and it's 70% of the time it's right about predicting survival. Well, is that good? Maybe. It depends on what we're using it for. I really want to be able to compare this model against another model. So what I'm going to do this time is I'm going to build a base rate model to compare my logistic regression model to. So what I'm going to do for my base rate model is real simple. I'm going to create a model that all it does is, given some set x, it's just going to predict that everyone dies. So it's going to return all zeros. All right, so how accurate is my base rate model on the test set? So I'm going to take the test set that we've defined above, and I'm going to feed it into my base rate model, and y base rate is going to be the prediction, which is going to be all zeros. Remember, we're predicting everyone dies. And so then what we're going to do is I'm going to have this little function here that tells me, I'm going to use accuracy score, and what it's going to do is say y test, which is the true survived and didn't survive, and y base rate, which is the prediction, which is everyone dies. It's going to just divide those two and figure out what percentage of the answers are correct. And surprisingly, my model was right 61% of the time. Well, maybe that surprised you. Maybe it didn't. If you remembered, most people did not survive the Titanic sinking. So what that tells us is when most of the answers are in one class or another class, accuracy maybe isn't the best metric. All right, so let's train our logistic regression model and see if we can beat 61%. So I'm going to import logistic regression from sklearn linear model. And I'm going to define a new instance of the model. The two things that you really should specify are penalty, and this is going to be L1 or L2. This is the regularization parameter, L1 or L2 regularization, which you should have remembered from last week. You can pick either. I chose L2. And C is going to be the regularization parameter. And I'm going to start with 1. And then what you can do is you can try to increase this and decrease this and find a value that works well for your model. Okay, so I am going to call model.fit using my x train and my y train. So this is the independent variables and the dependent variable. And I'll get back a note saying, hey, just wanted to let you know your logistic regression has been trained. It's all set. All right, so now I can start using this model to make predictions. And so what I'm going to do is I'm going to use that exact same accuracy score metric. And I'm going to say, give me the accuracy score for the difference between y test, which is the true value, and then model predict x test, which is actually the y hat variable or the predicted variable. So if we compare the two of these, we find out that logistic regression got it right 73% of the time. It's really pretty good. So our base rate model wasn't very good, but you know, compared to logistic regression, but it did work actually surprisingly well. It probably looked better than it should, and that's because there were more zeros than 1 in our data set. So if we just guess 0, we can kind of cheat. But there are some better metrics that we can use. The first metric I'm going to talk about, or well, really the only metric I'm going to talk about, is AUC, or area under the curve. And then very closely related to AUC are the terms or ideas of precision and recall, which are also very similar and related to type 1 and type 2 errors in statistics. Precision is the fraction of correctly identified examples in a class, so it's the ratio of true positives to all the positives identified. And then recall is the fraction of observations classified in that class that were actually correctly classified. I have a little bit of an example here about fishing. You can imagine that if we were fishing for tuna and our net was very precise and it had high recall, we'll catch any tuna and only tuna, assuming we were fishing for tuna. If our net was very precise but we have low recall, we would catch 1 or 2 of the tuna, but most would escape. We'd let them by. If our net was very low precision but had high recall, then we would probably catch all the tuna, but we would also catch all the other fish too. And if our net was low precision and low recall, we should probably not fish. All right. So I'm going to show you how to use AUC score to compare these models. And I'm going to also use the classification report feature to show you precision and recall. And these are just better ways to compare models than using accuracy. All right, so you can see I'm doing the same kind of thing for both the base rate and the logistic model. In fact, I most certainly could have refactored this code, but that's for another day. Okay, so in general, what I'm doing is I'm saying I'm creating this AUC score. I'm using the function rock underscore AUC underscore score. And I'm giving it the true values and then again the predicted values, and it's going to give me an AUC score. And I'll cover what that means in a second. And then I'm also going to call classification report on it in the same way. So here you can see the base model, the everyone dies model, is only 0.5, which is actually the lowest AUC you could possibly have. And I'll talk about that more in a second. But basically what this is saying is this model is no better than random. And then the logistic model has an AUC of 0.72, which is pretty comparable, I believe, to its accuracy metric. That won't always be the case. So we can see here that it's much more clear that the logistic model is far superior to the base rate model. And the reason why is because AUC doesn't suffer from that class imbalance problem that I was talking about earlier. And since it does not, we can see the difference here. In fact, we can see, of course, and obviously, that we predicted in the base rate model none of the survivors, and there were 56 in the data set. So we did horrible in class 1, which was survived. That said, we managed to predict all of the people that perished, of course, because we said everyone perished. However, our precision in predicting perished was very low. Well, it was 61%. So 61% of the time, we were able to predict that people perished. Well, that's because 61% of the people died in our test set. Okay. If we go back to our logistic model, though, we can see that now we were much more precise in predicting people that perished. However, our recall, of course, dropped. But our precision on people that survived was 0.67. That means 67% of the time that someone survived, we saw that they actually did survive. And 64% of the time, if we said someone survived, they actually did. We correctly predicted this. This is the type 2 error, the false positive rate. All right, so I'm using this term kind of without giving you a lot of explanation. So what exactly is an AUC, or area under the curve? Well, I've got that right here, and this is an example of a graph of AUC. And what you can imagine is, given all of these possible examples in our training set, and here's the true positive rate and the false positive rate, this line shows if I used 0.2 as a possible threshold and said anything over 0.2 is going to be classified as survived, this would be about my performance. And so what we want then is we want a model whose true positive rate is very high and false positive rate is very low. In general, we tend to try and pick a point around here, and there's a couple of mathy ways to do that I won't cover, but if you're interested, email me and I can talk to you about it. And so what that in general means is that we want the point here to be as close to here as possible, because this is like a perfect model, right? This is 100% true positive and 0 false positives. So what that means is that the more this curve can look like this, the better. That means the model is better. And so if we imagine the area underneath this curve, that's the measure that we're talking about. So the more area under the curve, the better our classifier is, because the closer it gets to being over here on this point. So that should give you some intuition on that. How do you calculate that? Well, it's actually kind of hard, but the best way to do it is to use trapezoids. Because as you can imagine, the calculus is a little bit challenging here, because this is a really hard line to figure out the function for. Okay, well, so that is our very first logistic regression classifier. Hopefully that was interesting. Hopefully you have some ideas on how to measure classifiers. And later on in this week, you'll be building your own. Thanks.